Hey guys, I'm Shein, and welcome back to the channel. Now, I want you to take a look at this. This is a photo of the galaxy JADES GSZ 14-0. It is currently the most distant known object from us. Just think about that for a second. Its light traveled for 13 billion years just to reach our eyes. This image was captured by the James Webb Space Telescope. And the craziest part? We're seeing it as it was when the universe was only 280 to 300 million years old, right after the Big Bang. By the way, because the universe is constantly expanding, scientists calculate that this galaxy is now actually sitting about 33 billion light-years away from us. That's because the universe is expanding faster than the speed of light, at least according to our current models. That means, physically, humanity will never be able to actually visit this galaxy, since nothing travels faster than light. We all learned that back in high school physics. You gotta admit, those numbers are absolutely mind-blowing. But have you ever stopped and asked yourself, why is our universe so insanely huge? I mean, so vast that just trying to wrap our heads around its boundaries totally breaks the human brain. We literally can't picture these kinds of distances. Then again, we're basically just smart mammals living on a tiny rock on the outskirts of a totally average galaxy. Our brains just weren't hardwired for this kind of knowledge. Evolution didn't prep us one day to figure out the cosmos, the universe, and all this mind-bending stuff. To blow your mind even further, imagine this. If we tried to fly to JADES GSZ 14-0 on our fastest modern spacecraft, a Crew Dragon cruising at about 7.5 kilometers per second, or nearly 17,000 miles per hour, the trip would take about 594 trillion years. That's 43,000 times longer than the current age of the universe. But JADES GSZ 14-0 reveals a tiny fraction of the unseen. Beyond it lie even more distant cosmic structures, and their light will literally never reach us because of the accelerating expansion of the universe. So what is the true size of space? What lies beyond the observable horizon? Is the universe infinite, or is it just a piece of something much, much bigger? Today, we're diving into a truly extraordinary topic. We're going to try to understand what the edge of the universe actually is, and if it even exists at all. For our limited human consciousness, which was never meant to comprehend cosmic scales, the concept of an infinite universe is almost impossible to grasp. When I was a kid, I used to imagine the edge of the universe and think, what's on the other side? Is it a brick wall? A cliff you can fall off? But for astrophysicists studying the cosmos, there are very specific boundaries. For a theoretical physicist, their world is a pencil and a piece of paper. When I study a planet, I draw it as a tiny speck. A star, hundreds of times larger, I draw exactly the same way. A star cluster, a galaxy, the entire universe, it all fits into a circle with its own boundary. But a boundary of what? If I'm an observational astronomer, my telescope is literally a time machine. The deeper into space I look, the further back in time I see because light takes time to travel. If I'm a theorist, my universe is still limited to the screen in front of me. Nevertheless, there really is a hard limit to what we can explore. We call it the observable universe. Modern physics describes the cosmos in 4 dimensions, 3 spatial dimensions, length, width, and height, and time. Our telescopes can see incredibly far, but not infinitely far. There's a limit beyond which there are no objects, no galaxies, no universe for us to see. That is the observable universe. Time lets us rewind the tape of the cosmos. The further away an object is, the younger it appears to us. But there comes a point where theory tells us you can't look past here. Why? Because before that moment, conditions were so extreme that our current laws of physics just break down. For example, in the deep past, all cosmic matter was compressed. Today, it's expanding, which means it used to be incredibly hot and dense. How far back can we model this process? Only as far as our math allows. We've tested these equations in particle accelerators, like the Large Hadron Collider, smashing matter together at massive energies, but not at infinite densities. Physics has an absolute limit. beyond a certain point, we step into totally uncharted territory. Picture a really long piece of string. If you were a creature that could only live along that string, you'd think your world was 1D, one-dimensional. Could you see the end of it? If it's long enough, no. But if you could step out into the second dimension, like an ant crawling on a table, you'd see that the string actually has ends. From your 1D perspective, you couldn't see them, but an outside observer absolutely could. Similarly, it's totally fair to guess that our 3D world is embedded in a fourth spatial dimension, and hypothetical beings with this higher perspective could see boundaries to our cosmos that are invisible to us. They might even look at us like ants, forever trapped inside the limits of a 3D world, unable to peek past its horizons. It's a fascinating hypothesis, though we don't have hard proof just yet. But there are intriguing hints. Maybe gravity, the fundamental force we understand the least, is the key that actually feels this extra dimension. The catch is, we don't have a complete theory of gravity. Einstein's general relativity works flawlessly on planetary or galactic scales. But in extreme conditions, like the heart of a black hole, it falls apart. We need a theory of quantum gravity, which we just don't have yet. And maybe eventually, that's the theory that will reveal the true nature of the cosmic edge. Let's talk about the boundaries we actually do know. As astronomers, we are tethered to the power of our telescopes. The most powerful one today is the James Webb Space Telescope, our cosmic sentinel. Practically speaking, Webb defines the edge of our observable universe. Recently, the Webb team announced they found a galaxy with an unusually high redshift. In the images, it just looked like a blurry smudge. At those distances, you can't see any real structure. The redshift meant its light had been stretched out so much that it shifted into the infrared spectrum, which is exactly what James Webb is designed to capture. However, closer observations with other telescopes showed that the redshift wasn't actually that extreme. It was a mistake. The galaxy turned out to be much more normal and way closer than we originally thought. And you can't blame the astronomers. The bleeding edge of science always pushes through a thick fog of maybes, possibles, and probablys. The lesson here is that conquering new frontiers takes patience and a healthy dose of skepticism. So, as it stands, the absolute farthest confirmed objects we found, primordial galaxies, formed when the universe was only about 300 million years old. Let's talk about distances. Measuring them in miles or kilometers is basically pointless. The age of the universe is about 13.8 billion years. That's our benchmark. Nothing can reach us from a distance greater than that number in light years, because the universe literally didn't exist before then. The light from those very first galaxies has been traveling towards us for over 13 billion years. But here's the crazy part. That galaxy wasn't just sitting still. While its light was racing towards us, space itself was expanding. At first, it slowed down, but then, mysteriously, the rate of expansion started to speed up. Today, because of this accelerating expansion, that exact same galaxy, if it even still exists, would be sitting somewhere around 30 to 40 billion light-years away from us. We can't see it there right now, maybe future civilizations will, but we know it was there in the past. It fits perfectly onto our map of the observable universe. And this is where you need to grasp the most important concept. We are always at the center of this map. It's not cosmic ego, it's just pure geometry. From our perspective, the observable universe is a perfect sphere surrounding us, with a radius of about 13.8 billion light-years. We're in the center simply because we're the ones making the observation. That means you, me, and anyone around you. Heck, even the potted plant on your desk is at the exact center of the universe right now, at the same time as you. But we'll get back to that in a sec. This trips a lot of people up. At my lectures, folks always ask, where is the center of the universe? Where did the Big Bang happen? The answer is, It happened here, there, and everywhere, all at once. Our normal idea of a center, like downtown in a city, doesn't apply here. The Big Bang wasn't an explosion in space, it was an explosion of space. Is the universe infinite or finite? That's an open question. It could be finite, but have no edges, kind of like the surface of a balloon. We love a good analogy in science. Picture an ant crawling on a balloon. It'll never find an edge and will probably think its world is infinite. But if it were smart enough and kept walking, it would eventually circumnavigate the whole thing and realize its world is finite but unbounded. Now, what if that balloon is being inflated at the same time? The ant keeps walking, but it never gets back to where it started because the surface is growing faster than it can move. There will always be new territory ahead. Our universe could be just like that, forever expanding, making it functionally infinite to us. The farthest regions are moving away from us faster than the speed of light, so their light will never, ever reach us. Our observable universe will keep growing, but only up to the limit of the light that manages to reach us. We, as physical beings, capped by the speed limit of light, will never be able to reach the edge of the universe, whatever it might look like. The leading theory says that in the very first fraction of a second of its existence, the universe went through a phase of hyper-fast expansion called inflation, which instantly made it colossal. But what about the theory of relativity, you might ask? Nothing travels faster than light. Well, Einstein's theory isn't broken here. Space itself isn't moving, it's expanding, and it can do that faster than light. The speed of light only acts as a speed limit for objects traveling through that space. Bringing it back to things we can actually see, the most distant object we can observe is billions of light years. Just 2 centuries ago, the most distant object known was Saturn. That was it. The leap we've made is absolutely staggering. And remember, we aren't seeing these objects as they are now, but as they were back then. Newborn, tiny, chaotic galaxies that will eventually merge into giants like our own Milky Way. Staring out at the cosmic horizon means looking deep into the ancient past of our very own home.
And this brings us to the inevitable question. What lies beyond the edge of our observable map? Can future astronomers ever hope to peek past it? Will the expanding universe eventually collapse back in on itself in a big crunch? Or will it just fade away forever into cold, dark silence? Right now, the outlook is pretty grim. Everything points to the expansion continuing forever, dragging galaxies apart into darkness and freezing cold. But our understanding of the cosmos has changed so many times, it'd be pretty arrogant to claim anything with 100% certainty. We'll leave that ultimate answer to future generations of cosmologists. After all, our sun has about 5 billion years left to shine. We've got plenty of time to do the science. Going back to our map analogy, where exactly are we? Our pale blue dot, the solar system, our galaxy, we are always at the absolute center of our own observable map. Our galaxy is part of the local group, which in turn is just a speck of dust inside a massive supercluster. Zoom out to the scale of hundreds of millions of light years, and the universe actually looks surprisingly uniform, kind of like cosmic sea foam. And no, we are not on the outskirts of the observable universe. We're right smack in the middle of it, because the sensor is defined by the observer, like we talked about earlier. No matter where you are in the universe, you'd see the exact same thing. Space expanding away from you in all directions, placing you right at the center of your own observable sphere. It's a totally counterintuitive concept. Honestly, I have a hard time wrapping my own head around it. We tend to think that because we live in the suburbs of our galaxy, we must live on the edge of reality itself. But that's simply not true. The exact spot where you are sitting right now, in the moment of the Big Bang, was part of that infinitely dense, infinitely hot singularity. If you crushed all the matter and energy in the observable universe down to its original state, it would fit into something smaller than an atom. Just let that sink in. The best mental model for this is a loaf of raisin bread rising in the oven. We are like the raisins in that dough. As the dough expands, every raisin moves away from every other raisin. There is no center to the dough itself. The sensor is everywhere and nowhere. Every single raisin would watch the others moving away, making it feel like it's the center of the expansion. It's a profound feeling, one that really humbles you when you realize our true scale in the cosmos, and it's just something we have to learn to live with. I am incredibly grateful that you spent this time with me today, and I really appreciate it. I hope this little talk made space and the universe feel just a bit closer and easier to understand, because that is exactly what this channel is all about. Thanks for watching, and I'll see you in the next one.